Welcome back to the Deep Dive, where we plunge into complex research and emerge with the essential knowledge shortcut you need. Today, we are putting on our seismic exploration hats and looking thousands of feet below the ocean surface. Our target is the deep layers of the Earth. And the mission is, well, it's a billion-dollar question that defines modern energy exploration. How do we map the geological subsurface layers accurately, identify crucial resources like oil reservoirs, and do it all at a pace that is, economically viable?
It is arguably one of the most challenging inverse problems in applied physics. The stakes are immense, and they're primarily driven by the energy sector. Their need is really twofold. First, to maximize economic yield by finding resources efficiently. And second, and this is just as important, to minimize environmental impacts by ensuring drilling is highly targeted, based on rigorous, accurate prior geological knowledge.
Right. If you drill blindly, you risk disaster and you waste just astronomical amounts of time and money. What they need are high-resolution, two-dimensional images, essentially an ultrasound of the Earth's interior that shows exactly where the layers are, how they fold, and where they might fracture.
Precisely. And the traditional method for generating those images is what we call the seismic method. It's been the gold standard for decades, and it relies on capturing mechanical waves. These waves are generated by artificial sources, think specialized cannons or vibrators, and the resulting echoes are captured by thousands of sensors. They can be on the sea surface, on the sea floor, or even towed behind ships.
So if we can simplify the physics for a moment, we're treating the Earth as a giant acoustic medium, right? We send sound waves down and we listen for the changes in speed as those waves bounce off or pass through different materials.
That's the fundamental assumption. We assume the Earth behaves acoustically. The critical parameter the sensors are measuring is the speed of wave propagation. As a wave moves from, say, soft recent sediment into dense old rock, that speed changes dramatically. By capturing those time differences and speed variations across a massive array of receivers, you can begin the long, complicated process of inferring the structure beneath.
That seems incredibly powerful on paper, but this is where the computational physics intervenes and, I guess, slams the brakes on efficiency. What is the fundamental technical reason why the traditional seismic method is so slow and so costly?
It boils down to the fact that the process of converting recorded wave characteristics into a geological image is classified as an ill-posed inverse problem.
Okay, let's unpack that term ill-posed inverse problem because it's central to why this entire field is looking for an AI solution. What does it mean for an engineer trying to find an oil trap?
In simple terms, an inverse problem is trying to infer the cause, the underground structure, from the effect, the seismic wave data we recorded. It's the opposite of forward modeling, where you know the structure and predict the waves. The ill-posed part means that a solution is exceptionally fragile. If you have noisy data or if your initial assumptions about the geology are slightly off, the resulting calculated model can be wildly inaccurate. It is highly sensitive to the initial conditions you define.
So training measurement errors or bad initial guesses can just spiral into massive unusable maps. And because of the sensitivity, solving it requires brute computational force and constant iterative adjustment, which translates directly into cost and time.
Exactly. And when you factor in the massive scale, we're talking petabytes of raw seismic data from a single survey. The computational effort needed to refine a model until it is robust and trustworthy is prohibitive. It often means months of computation on massive supercomputer clusters, and the dedicated labor of highly specialized geophysicists just to move from raw data to a preliminary map. The traditional iterative optimization methods just take too long and are too prone to getting stuck in those local minimums of inaccuracy.
So if WINTs or months are the current standard for high accuracy mapping, what is the revolutionary alternative this research proposes?
The alternative is automation via deep learning. The study focuses on using specialized artificial neural networks, or ANNs, to perform automatic segmentation. So instead of iterative optimization, the network is trained to instantly predict the velocity model, the map based on the seismic shots.
And the specific technology they focused on, which we'll dive deep into, is UNet.
Yes. The mission was to validate if a specialized UNet architecture, originally designed for medical imaging, could be repurposed to perform seismic velocity model inversion effectively and efficiently.
And what's the headline we're working toward here? What statistical success did they achieve that suggests this is a viable path forward?
The target outcome was clearly met. When evaluated using the Sorensen-Dice coefficient of metrics specifically designed for measuring image similarity, the network achieved similarity rates reliably above 70%, actually approaching 75% accuracy. For an automated solution tackling such a complex, ill-posed problem, that 75% is a massively compelling result. It validates the potential for a near-instantaneous mapping process.
That sets the stage beautifully. Before we celebrate the AI solution, we need to spend a little more time cementing the challenges that AI is trying to circumvent. Let's move into section 2, seismic velocity inversion and why the traditional approach is, well, such a headache.
We talked about the acoustic medium assumption. Let's explore what that really means in practice for geophysics. When we assume the Earth is acoustic, we are primarily concerned with compressional waves, P waves, which travel through fluids and solids. The speed of that wave is what determines our velocity model.
But the Earth isn't perfectly acoustic, it's elastic.
And that's a crucial limitation. Real-world geology transmits both compressional waves and shear waves, or S waves. S waves are waves that oscillate perpendicular to the direction of travel, and they carry vital information about rock rigidity. Traditional seismic methods often simplify the mathematics by neglecting these S waves, especially in deep water environments. This simplification speeds up the forward modeling, but it immediately introduces uncertainty and error into the inversion process. You're trading accuracy for solvability.
So traditional seismic velocity model inversion is inherently flawed because the physics models are a necessary simplification of reality. And this is the core technique the oil and gas industry relies on to infer internal subsurface structure.
Precisely. The inversion technique is trying to build a picture of the subsurface structure and the wave speeds within it. And as we discussed, traditional techniques rely heavily on optimization methods.
Let's drill down into that optimization process. What are the two crucial steps required in the traditional model, and why do they cause these computational bottlenecks?
The two steps are defining the initial model and minimizing the objective function. Step 1 is the human element. The geophysicist must define an educated guess, a starting model. This is already difficult because they rarely have sufficient initial information about the geological structure of a new area. If they start too far from the truth, the algorithm might never find the correct answer.
And step 2, minimizing the objective function, is the long, costly computational grind.
It is the grind. The objective function quantifies the mismatch between the seismic data you recorded and the seismic data your guessed model would generate. The algorithm must continuously adjust the parameters of the model, the layer boundaries and speeds, and run millions of computationally intensive forward models to see if the prediction improves the match. It's like searching a vast, bumpy landscape for the lowest possible valley, representing the smallest error.
And the major limitations that prevent this process from being fast and reliable.
We face two primary foes. First, noise sensitivity. Seismic data is messy. It's collected under real-world conditions with currents, weather, and background geological noise. Traditional optimization algorithms struggle immensely to differentiate the subtle geological signal from the overwhelming ambient noise. Small noise features can trick the algorithm into thinking it has found a true boundary when it hasn't.
And the second foe is related to that bumpy landscape you mentioned, the local minima.
Yes. Because the search space is so vast and complex, the algorithm can easily get stuck in a local minimum, a shallow dip in the air landscape. It thinks it has found the best possible answer, but in reality, a much better solution exists just over the hill. And the algorithm doesn't have the power or the initial momentum to climb out of that dip and find the true global minimum. This is why a good initial guess is so vital, and why, if you lack one, the process fails spectacularly.
The computational bottleneck is becoming incredibly clear. It's not just that the calculations are complex, it's that you have to repeat them millions of times, often over days or weeks, just to avoid a local minimum or mitigate the effects of noise.
That's the key distinction that AI seeks to exploit. Traditional inversion is an iterative refinement process, requiring the rerunning of massive simulations. Deep learning, once trained, is a single, instantaneous prediction. You replace weeks of refinement with milliseconds of inference. That efficiency gain is why this study holds such potential value for the industry.
That makes the drive toward automation completely illogical. So let's pivot now to the solution, the deep learning toolkit. We are moving into section 3, where we introduce the specific technology that promises to crack this problem. We are talking about artificial neural networks.
Indeed. Artificial neural networks, or ANNs, are computational models fundamentally inspired by the biological structure of the human central nervous system. They are designed to excel at pattern recognition and complex mapping tasks that traditional linear algorithms really struggle with.
Let's define the structure for anyone who needs a quick refresher. What are the fundamental components of an ANN?
The architecture is built on layers of interconnected processing units, which we call neurons. Think of it like a chain of command. You have the input layer, which receives the data, in our case, the seismic shots. Then you have one or more hidden layers where the complex nonlinear processing and feature extraction occur. Finally, the output layer provides the network's prediction, which in this study is the high-resolution velocity map.
And the connections between these neurons, the links that determine how information flows, are governed by what are called synaptic weights. That's what defines the network's knowledge, right?
Exactly. And the process of defining those weights, the learning,
Hmm.
is where the real magic happens, through a process called backpropagation.
Can we go beyond the simple definition of adjusting weights? How does backpropagation actually allow the network to turn a seismic shot into an accurate geological map?
Backpropagation is really the engine of learning. During training, we feed the network a known input, a simulated seismic shot, and we have the known correct output, the ground truth velocity model. The network makes a prediction, and we calculate the difference between the prediction and the ground truth using an objective function. In this case, that's the mean square error, or MSE. This gives us the error.
So the MSE tells us how wrong the network was.
Precisely. Now, backpropagation uses calculus, specifically the derivative of that objective function, to calculate the gradient. The gradient tells us two things: the magnitude of the error and, crucially, the direction we need to adjust the weights to reduce that error. The process then propagates that error signal backwards through the layers, adjusting the weights of every single neuron slightly so that the next time the network sees a similar shot, its prediction will be closer to the ground truth. It's a continuous, self-correcting feedback loop.
That detailed learning capacity is what has made ANNs so ubiquitous. We see them everywhere. Speech recognition, image classification, even generating complex art. But we also have to acknowledge their inherent weaknesses.
They are powerful tools, but they do have key limitations. The primary one is data hunger. ANNs typically require vast, clean datasets to train effectively and generalize well to new, unseen examples. If the training data is sparse or doesn't cover the full range of possibilities, say only simple geology, the network will fail when confronted with complex real-world data.
And sensitivity to noise.
They can be highly sensitive. While noise is a challenge in traditional methods, ANNs can sometimes latch onto noise as a distinguishing feature, leading to spurious correlations. They might interpret a noisy measurement as a fundamental geological feature, which harms accuracy.
And the limitation that often makes scientists nervous, the black box problem.
The interpretability challenge. Because the network's knowledge is encoded in millions of subtly adjusted weights and complex nonlinear interactions across the hidden layers, it is nearly impossible for a human scientist to point to a single weight or connection and say, that is how it knows there is a fault here. When an error occurs, diagnosing why the network failed can be incredibly difficult. In a conservative field like energy exploration, where millions are on the line, that lack of interpretability can be a bigger hurdle than a 25% error rate.
That's a powerful point. Now let's zoom in on the specific flavor of ANN used here. The convolutional neural network, or CNN, and its specialized relative, UNet.
CNNs are a variant of ANNs explicitly designed to process visual data image datasets. They use what are called convolution layers to extract spatial hierarchies of features like edges, textures, and eventually complex shapes. A standard CNN typically performs classification.
Meaning, if I give it a seismic image, it might output a label. This image is 90% likely to be a salt dome.
Exactly. Classification gives you a single category or label, but for geological mapping, a label just isn't enough. We need the exact boundaries. We need segmentation. This is why UNet was chosen.
UNet was developed back in 2015 for biomedical images, specifically for segmenting cells and tissue boundaries. That seems like a long way from subsurface rock layers. Are we confident that translating an architecture designed for soft biological structures will work on sharp geological interfaces?
Well, that is the critical question this research addresses. UNet is a powerful segmentation tool because its output is not a label, but a pixel-by-pixel map and image. It tells you exactly which pixels belong to which class of rock layer. Its name comes from its distinctive U-shape architecture.
What does that U-shape represent architecturally?
The U-shape is composed of two symmetrical paths: the encoding path on the left side, which is a contracting path, and the decoding path on the right side, which is an expanding path. The encoding path is a standard CNN that repeatedly applies convolution and pooling layers. Pooling layers reduce the spatial size of the image, essentially distilling the image down to its core features, getting the big picture concept of the geology.
So you sacrifice detail for general recognition.
Precisely. You recognize the general shape of the fold, but you lose the fine-grained location of the edges. If the network only had the encoding path, the final output would just be a low-resolution map.
So how does UNet recover that crucial high-resolution spatial information? That's where the skip connections come in, right?
The skip connections are the architectural genius of UNet. They are direct links that bridge corresponding layers in the encoding path to the decoding path. As the decoding path attempts to reconstruct the full-resolution image from the highly compressed feature map, the skip connections feed back the fine-grained spatial data, the high-resolution edge information that was lost during the pooling operations.
Okay, so the decoding side gets the abstract features from the bottom of the U, but the skip connections remind it exactly where those features were spatially located in the original input image.
That's the key to high-accuracy segmentation. It ensures that the final output, our velocity model, retains the sharp boundaries and structural detail necessary for accurate geological assessment, which is paramount for deciding where to sink a drill. Without skip connections, the map would look blurred and imprecise at the layer interfaces.
We've established the necessity of automation and the suitability of the UNet architecture. Now let's move into the practical details of Section 4. Methodology. How do they actually train this AI to see underground?
Well, the foundational task was creating the data. Since real-world labeled geological data, meaning seismic shots, paired with the perfect known velocity model is rare and expensive, the researchers had to rely on simulation. This is what's called synthetic data generation.
Walk us through the input and output data structure for the training phase. What exactly were they feeding the network?
The input data was the seismic shots generated by the simulated sensors, which contain the complex wave patterns. The desired output, the target, was the resulting velocity model, the 2D image of the subsurface. To generate these paired examples, they needed a specialized tool.
That tool was DeepWave, a wave propagation simulation package. Why was DeepWave so essential?
DeepWave is critical because it performs the necessary forward modeling. You input a known geological structure, a map of layers and speeds, and DeepWave simulates exactly how a wave would travel through it and what the sensors would record. This creates the training pair, a known input shot and its known perfect ground truth model. Crucially, DeepWave also supports the necessary calculations for backpropagation, allowing the network to calculate the required gradients during training.
Let's detail the data size and complexity, because this directly influences the network's ability to generalize.
The simulation environment standardized all models and shots onto a manageable grid size of 128 by 128 dimensions. This choice is pretty typical for initial proof-of-concept research. It's large enough to be geologically representative, but small enough to manage the computational load, especially during early testing on platforms like Google Colab.
And they tested two different dataset sizes to assess how data volume influences efficiency and accuracy.
Yes, a smaller set of 300 simulated elements and a larger set of 1,000 simulated elements. The rationale here was to see if the network, even with the relatively small 1,000 element set, showed signs of improved efficiency or generalization capacity. It provides a benchmark for future large-scale data generation.
They also deliberately varied the geological complexity within those data sets. This seems essential for measuring the network's robustness.
Absolutely. They defined two main levels of complexity. First, the simple set, which featured basic, well-behaved models without major geological defects containing straightforward layering. Second, the complex set, which was designed to challenge the network. This set included features like faults, erosion processes, fractures, and complex folds, which are much harder for any algorithm, human or machine, to accurately resolve.
So by training on simple models and then testing against the complex ones, they can see exactly where the network starts to fail.
That's the goal. The simulated shots also varied by parameters like the number, position, and spacing of wave receivers, ensuring the input data captured a realistic range of seismic acquisition scenarios.
Moving to the architecture itself, they didn't just use the standard UNet. They tested two specific models, the unmodified UNet and a modified version UNet Mod.
Correct. The standard UNet served as the control group. The second model, UNet Mod, was a subtle but important alteration. They deliberately excluded the skip connection between the first layer of the encoding path and the final layer of the decoding path.
Why exclude that specific connection? It sounds counterintuitive given how important you said skip connections are for detail.
It was likely an empirical test. That particular skip connection bridges the raw, highest resolution input data, the seismic shot, directly to the highest resolution output reconstruction, which is the velocity model. Researchers might hypothesize that including this raw information too early in the reconstruction process could sometimes introduce unnecessary noise or complexity, leading to instability rather than pure structural detail. They wanted to see if forcing the network to rely on the lower, deeper feature information resulted in a more stable prediction.
That makes sense. Test the robustness of the core feature extraction process without that highest level spatial bypass. Now, the practical computing environment.
The entire project was executed using Python on Google Colaboratory, specifically utilizing its powerful GPUs. GPUs are non-negotiable for deep learning training because their parallel processing power accelerates the massive matrix multiplication required for convolution and backpropagation by orders of magnitude compared to standard CPUs.
And what about the hyperparameters, specifically the batch size?
They empirically chose a batch size of 8 for both architectures. The batch size is the number of data elements, so 8 seismic shot and velocity model pairs, that the network processes simultaneously before updating its weights. This choice balances the need for efficient use of GPU memory with ensuring that the gradient calculation is representative of the overall dataset.
Finally, let's detail the evaluation metrics. We need to clearly differentiate between the metric used during training and the definitive metric used for the final test.
During the training and validation phase, the metric used was the mean square error, or MSE. As we discussed earlier, MSE calculates the average square difference between the predicted value and the ground truth. It's what the network is trying to minimize during backpropagation. To ensure the models weren't simply memorizing the training data, they employed cross-validation, dividing the dataset into 10 random batches. They used 64% for training and 16% for validation, iterating 10 times to check consistency.
And the true litmus test used on the held out 20% of the data was the Sorensen-Dice coefficient, or DSC. Why is the DSC the superior metric for this kind of mapping pass?
The DSC is essential because it is an image segmentation metric. It specifically assesses the similarity rate or overlap between two binary or multi-class images. In essence, the DSC is a variation of the intersection over union, or IOU, concept. If you imagine the predicted layer boundary as one area and the ground truth layer boundary as another, the DSC measures the ratio of the area they share, the intersection, compared to the total area they cover together, the union.
So a DSC of 1.0 means perfect overlap. The predicted map is identical to the ground truth. A DSC of 0.0 means zero overlap.
Exactly. Since the values range from 0.0 to 1.0, it gives a really easily interpretable visualization of success, which we can translate directly into a percentage similarity rate. It's a far more definitive measure of mapping accuracy than a simple overall error rate.
This rigorous methodology sets the stage. Let's move into Section 5 and analyze the key findings, what the networks learned and where they still struggle. We start with stability, looking at those loss function curves.
When reviewing the loss function curves, the initial observation is highly encouraging. Both the training and validation curves showed a smooth, consistent decline and eventual stabilization. This indicates that neither network exhibited signs of overfitting, where the model memorizes the training data but fails on new data, or underfitting, where it fails to learn the patterns adequately. The solutions were robust and stable.
They also required roughly the same amount of time for the loss functions to stabilize, but there was a subtle yet significant difference in the stability between the two architectures during validation.
Yes, the modified architecture, UNetMod, displayed a validation curve that was much more tightly clustered around its training curve compared to the unmodified UNet. This suggests that the UNetMod architecture was slightly more robust in generalizing its knowledge to the validation data.
So, removing that top layer skip connection didn't hurt. If anything, it seemed to streamline the generalization process, leading to more consistent performance.
That's the inference. It points to the possibility that in this specific seismic context, relying on the deeper, more refined feature maps passed through the U-shape was more beneficial for stability than including the raw, possibly noisy, spatial details from the first layer.
Let's move to the quantitative results, the core performance metric captured by the DSC. What was the overall similarity rate achieved?
Both networks achieved satisfactory results, which firmly validates the potential of ANNs for this application. The overall similarity rate was consistently approximately 75%, meaning the DSC values were reliably above 0.70.
75% is a strong figure, especially when you consider the computational speed gain we talked about earlier, replacing weeks of iterative computation with seconds of inference. But comparing the two architectures using the DSC, UNetMod again demonstrated a stability advantage.
Yes. While the average performance was similar, The UNet mod exhibited greater consistency in its DSC scores across the different cross-validation folds. The unmodified UNet showed slightly more variability in its predictions when tested on different subsets of the data. Stability is highly valued in industrial applications. Consistency means predictability.
Now we get to the visual biases, which are fascinating because they reveal exactly how the network is thinking. The UNT mod consistently generated a specific, unexplained feature.
This is perhaps the most telling outcome captured in the visual difference maps. The UNet mod consistently exhibited a distinct prediction bias, a circular artifact that appeared in the upper right region of the difference images.
A circle appearing where it shouldn't be. What did the researchers theorize was the cause of this specific artifact?
They suggested it was a classic case of data bias leading to overgeneralization. The training dataset tends to contain a geological fault located near that specific upper right region. The network learned this pattern so strongly that it began inserting this feature, the circular artifact, which approximates a fault structure, into all predicted models, even those that, according to the ground truth, had clear layering there.
It's like an artist who learned to always include a small cloud in the upper right corner of every painting, and now they draw it in automatically, even on a clear day. It's an error, but it proves the network is highly capable of recognizing and generalizing complex features.
Exactly. It shows the black box isn't completely opaque. Sometimes its flaws illuminate its processes. Fixing this specific artifact would involve either removing the biased samples or generating far more diverse data that contradicts the network's learned expectation in that area.
Let's look at how geological complexity challenged the networks. How did the networks handle simple layers compared to models with complex folding and faulting?
The networks handled simple models, basic, horizontal layering without major defects, with high satisfaction and accuracy. Velocity models containing only fold, curved, layered structures were also generally predicted satisfactorily.
But even with the folds, there was a specific critical loss of detail that relates to the ultimate usability of the map.
This is the crucial finding regarding the limitations. When predicting folds, the models consistently struggled to reproduce the sharp transition or interface between layers. Instead of sharp, discontinuous boundaries that characterize real geological layers, the network predicted smooth gradients. The transition from rock A to rock B looked blurred.
If the boundaries are blurred, the engineer cannot pinpoint the exact depth or location of the layer interface, which is vital for drilling. It undermines the precision promised by high-resolution mapping.
It absolutely impacts precision. The network successfully recognized that a fold was present, but it failed to define where its physical boundary lay with crisp accuracy. And the accuracy dropped further when the networks faced the highest complexity models, those containing both faults and folds combined.
How did the networks handle that maximum complexity?
In those highly complex scenarios, while the network could generally identify the presence of the structures, the faults themselves became ambiguous or poorly defined. The accuracy was lower, and the utility of the resulting map decreased. While basic identification was possible, the precise geometry and kinematics of the faulting, which are crucial for understanding fluid flow and reservoir potential, were not resolved accurately.
So the headline remains the stable 75% similarity rate, which is a massive win for speed and automation. But the fine-grained details, the sharp boundaries, and complex fault geometries are where the current UNet architecture hits a wall.
That's the tension of the results. The automation works extremely well for the bulk of the problem, but the specific high-stakes areas of transition and discontinuity require further architectural intervention.
That brings us perfectly to our conclusion in Section 6 and the necessary future directions. The core finding is that ANNs are a promising, stable foundation for velocity model inversion.
The conclusion is firm. ANNs provide a satisfactory and stable automated result for a classically ill-posed problem, regardless of whether the standard UNet or the slightly modified UNet mod was used, with a modified architecture showing slightly better stability.
Now we need to connect those remaining challenges, the circular artifact and the blurred boundaries, directly back to the research agenda for the future.
The first, most immediate task is addressing that specific prediction bias. They must investigate the cause of the circular artifacts in the UNet mod predictions. This isn't just about cleaning up the image, it's about refining the training methodology or potentially altering the loss function to penalize those overgeneralized features.
And the second major push is crucial. Tackling the complexity limitation we saw with faults and folds. How do they plan to stop the network from generating those smooth gradients instead of sharp interfaces?
By introducing a physics-informed stage. This is the next revolutionary step in deep learning for scientific applications. Instead of treating the network purely as a pattern recognizer, this stage embeds known physical laws, the actual equations governing wave propagation and geological constraints, directly into the learning objective.
So the network is trained not only to minimize the difference between its prediction and the ground truth, the MSE, but also to minimize the degree to which its prediction violates known physics.
Exactly. This constrains the network's guesses, making them more physically realistic. A physics-informed network would be less likely to produce a smooth, blurred gradient where a sharp discontinuity, like a fault, is required by the laws of geology. This optimization phase is intended to be specifically targeted at those highly complex models containing faults and folds where the current network struggles most.
And the final perpetual requirement for scaling this solution is the dataset size.
Generating more training data is non-negotiable. The current dataset of 1,000 elements, while sufficient for validation, remains a significant limiting factor. To enhance the generalization capability and move the accuracy beyond 75%, especially in those complex fault-fold models, a much larger, more diverse library of synthetic geological models must be generated. That data is the food and water for the hungry ANN.
Let's pull back and summarize the significance for you, the informed learner. What does this study mean for the field of seismic imaging?
This study provides a credible, validated path away from months-long, computationally demanding, and initial model-sensitive inversion methods. It validates the use of specialized deep learning tools like UNet for automated, high-accuracy subsurface mapping. For the energy industry, this means drastically accelerated exploration timelines, reduced computational expenditure, and improved precision, which directly lowers operational risk and improves resource management. It is a genuine paradigm shift from iterative refinement to instantaneous prediction.
The groundwork is complete. The next phase is refinement and ensuring that the automated predictions are trustworthy enough to guide actual drilling decisions. That is a phenomenal summary of a highly technical piece of research. As we wrap up this deep dive into the world of AI-driven geophysics, let's leave you with one final thought to consider, building on the key limitation we identified.
The limitation being the smooth gradients replacing the sharp layer boundaries.
Right. We know that the network is stable and 75% accurate overall, but it struggles with discontinuities. The crisp boundaries between ocean floor layers are the geological equivalent of street signs. They signal critical transitions and potential resource traps. They are non-negotiable for accurate assessment.
If the AI blurs those lines, the value of the map drops dramatically for practical application.
So given that the current UNet prediction models tend to lose this layer interface information due to the predicted gradients, how might future advancements in AI architecture, perhaps new loss functions specifically designed to heavily penalize blurriness, or even architectures that actively favor sparsity and sharp transitions, how might they specifically focus on recreating those discontinuous interfaces?
It raises the question. Does the next generation of deep learning for geophysics need to move away from favoring smoothness, which is a common trait in many image processing networks, and actively be engineered to recognize and value the precise geometry of a sharp, abrupt change?
It is the ultimate challenge, teaching an AI not just to see the shape of the mountain, but to draw the exact critical fault line that defines its structure. That pursuit of boundary-accurate mapping is the next frontier for ensuring these automated systems become the true industry standard. We'll leave you to mull over that intersection of deep learning and deep earth physics. Thanks for joining us for the deep dive. We'll see you next time.